Hey guys, welcome back. We're looking at normal models today for AP statistics, and so what I'd like to do is maybe just go over what a normal model is, what a normal model is, how we'd use it, what we use it for, and some really interesting things about it that that make it interesting. So let's first talk. Let's talk about maybe a scenario first that we would see. Let's say I got a bunch of people, and they are, maybe I'm doing, I'm gathering some data on how many cat videos. No, how about how much time they spend watching cat videos? Because that seems to be a popular thing to do now online is watch cat videos. So, I think if I did these math videos and I had like a cat right next to me, maybe I'd get like 1 million views. Maybe for the next one, I'll bring in a cat. So we've got these people, and they watch cat videos, and I went to someone's house and watched them watch cat videos, and just timed it, and then I had someone else and I timed their cat video watching, and timed their cat video watching, and what happened was I drew a model, not really a model, but I drew a histogram of those times. So this is like this is the time watching cat videos, right? Watching cat videos, and they watch cat videos, and let's say I have a few in here. They watch these videos, and I got a little dot plot here, and there's a lot in the middle, and maybe around most people watch the cat videos for 15 minutes. A lot of people watch cat videos, right? And they keep watching. Some people don't watch that many cat videos, and some people watch. They just obsess over cat. They just watch cat videos all the time. So eventually, I've got this histogram, and it's about it's unimodal and about symmetric. So the thing about normal models is that they can only be used with symmetric data, and we don't want to use them with skewed data. They don't really, it's a model, so it's modeling what's happening for the entire population. Even though we got the sample, the normal model helps us see what's going on with the entire population. So we're thinking, all the people watching cat videos are kind of going to look like this. Okay, so we're just looking at the data that we've got, and we decide that after we plug in this into our calculator and find the histogram, and I'm taking some ideas on what's going on with these people watching their cat videos, I find that the average of time that people are watching these cat videos are 15 minutes. Spending a lot of time on that. So it's about 15 minutes, and that I find a standard deviation, and then it actually comes out to be 3 minutes. So people are on average, the average distance from the mean on average is about 3 minutes. So if I go above like one standard deviation above 15 minutes, and I've got about right here, it's like 15 is 18 minutes, right? Because it's 3 more minutes, and then I go back here 1, and then it's what's that? 12 minutes, right? So then I'm going 3 minutes each time. Let's go one more. That's 9 minutes, and then we'll add 3 more minutes, and that's 21 minutes. And soon enough, people are watching a lot of cat videos for 20 minutes. I think 21 minutes is a long time to watch a cat video, but say what. So 9 minutes. Let's go one more down here and get 6 minutes, and then 24 minutes. All right. So these are each of this is a standard deviation away from the mean. This is how far on average people are from an individual's from the average cat watching video time. So if I drew a curve, kind of like this. This curve is going to be symmetric. It's going to model the population data here pretty close. So what I would do is I'd say what my mean is. If this was the population, this is all everybody watching the cat videos. My mean is going to be 15 minutes, right? 15 minutes of watching cat videos, and my standard deviation is going to be 3 minutes. So I've got a mean of 15 minutes and a standard deviation of 3 minutes from watching this cat video. This curve, this symmetric curve, is called the normal model, and they're really really important things about this normal model that we want to take a look at. So what's happening here is that that right in the middle, right in the middle is the average, right? That's the mean. And if we're these are all the data, right? These are all the people in our little cat video survey or experiment, not experiment, but data that we got. I don't want to use the wrong words here. And what happens is that when we look at this through a normal model, one standard deviation from the mean at 18 right here, and between 18 and 12 minutes, this actually captures 68% of our data. So 68% of our data are in between 12 and 18 minutes. In fact, we could keep going out each standard deviation and we're going to capture more and more and more of our data, right? I mean, it seems like soon I'm going to capture all of my data. Well, it turns out that if we go another standard deviation, this 2 standard deviations is going to capture 95% of our data. So we've got 68% within 1 standard deviation. 95% of our population that are watching cat videos are going to watch them between 9 and 21 minutes. 95% of them. If we go one more standard deviation, three standard deviations out, okay, away from the center, the mean. This is symmetric, right? We go all the way out to here, We pretty much look like we've got most of our data, right? Most of it's right there. This right here, between 3 standard deviations, is 99, okay, 99.7% of our data, 99.7% of our data exist within 3 standard deviations of the mean. Oftentimes, this is called the 68, 95, 99.7 rule. Okay, so let me. We got all this cat data up here. I want to clean this up a little bit, okay? So we can really see what's going on with this rule. So, thinking about the situation of cats, okay? This is time watching videos of cats. 1 standard deviation away from the mean. Okay, 1 standard deviation away from this is 68% of the population. That means if we were to gather all the people all the people that are watching cat videos, 68% of those people are going to be watching between 12 minutes and 18 minutes of cat videos. Between 9 minutes and 21 minutes, which is 2 standard deviations from the mean, I'll just put mu right here so we know that that's the mean, is 95% of the data. That's a lot. It's a lot. That's most of it, right? 95% of our data lie between 9 minutes and 21 minutes. That's a lot of our data. That's most of our data, right? 99.7% lie between 3 standard deviations. Okay, this is mu, right? This is mu. Mu is no standard deviations from the mean because it is the mean, right? This is a 1 standard deviation, and we write it like that: 1 sigma, 2 sigma, 3 sigma. I can write this going backwards here, so -1 sigma because it's less than the mean. -2 sigma, -3 sigma, right? So the farther away we get from the mean, the more of the population, the more of the data that exists between those two standard deviations. This is what we call a 98, 95, 99.7 rule. All right. So what we're going to be interested in here is we're going to be interested in doing a lot of things and seeing, let's say I watched 19. Ooh, I squeaked there. Let's say I watched 19. I was in the video thing too, and I watched 19 minutes of cat videos. What does that tell us about where I stand in relation to the population? Or maybe I want to know how many people in the population spend less time watching cat videos than I do. Less time watching cat videos than I do. That's actually called a percentile. So if I have a number, all right, and I want to know the percent less than what I am, or what this value is, that is a percentile. So a percentile, okay, is the percent less than. You know, some of you have always seen, you see your SAT reports or your PSAT reports, and they say, hey, you're in the 92nd percentile. Well, what does that mean? That means, well, 92%, if you're in the 92nd percentile, that means 92% of people like you scored less than you did. Pretty good, all right? If I'm in the 50th percentile, I'm right average, right? I'm average. So we're gonna do some things where we have to find the percentiles. The other thing to notice is when we're dealing with the normal model. I'm going to draw this normal model a little bit bigger. Actually, I'll just draw underneath here. We use Z-scores in the normal model because let's say I'm comparing the number of cat videos, time in cat videos, with the speed at which people are, watching, something else. So basically what I'm saying is I'm trying to compare time with speed, and really that we can't compare those, but if we had some way of standardizing that measurement, we could compare that. And that's called a Z-score. And the Z-score is how far away from the mean are we? Okay, this is Z-score right here is -3. This Z-score right here is -2. This Z-score is -1. The Z-score for mu is 0, because you know what? I'm not any far from the mean. This is +1, +2, +3. So the further away I get from the mean, the higher my Z-score is. Well, either negative or positive. Sometimes we just say your Z-score is pretty big, or it's very, very small. It's negative. So how far is too far, right? Well, if we're looking at the 98, 95, 99.7 rule, you could think that 95% are within 2 standard deviations of the mean. 95%, that's a lot of data. It's most of your population. In fact, you only have 5% of the population that's not within 2 standard deviations. You have 2.5 over here, 2.5 over here, because the whole thing has to be 100. So 2.5 plus 2.5 plus 95 is 100. That's a pretty small amount of population that's outside 2 standard deviations. It's kind of weird, If someone came up to you, I watch 23 minutes of cat videos, in a very serious voice like that. 23 minutes of cat videos. 23 is right here. Guy, you're pretty. There are a lot of people that don't watch cat videos like you do. You're kind of strange, That's a lot of cat videos. Anything outside of 2 standard deviations, anything outside of 2 standard deviations from the mean, outside of 2 standard deviations of the mean, it's kind of weird, That's kind of odd. Maybe even call that an outlier. You kind of frighten me. You're 2 standard deviations away from the mean. I wouldn't be frightened by that, but look, the point is that's outside the realm of what we normally see, right? So anything outside that would be an outlier. Okay, so let's kind of sum up the whole thing. There are a lot of things in the next video I'm going to actually do a few problems that we would see in an AP Stats class, where we would use the normal model to maybe find a percentile. Maybe we're looking for a Z-score associated with 98%. Maybe we know the Z-score, and we want to know how much of the population is between 2 Z-scores. Maybe like the Z-score is like 1. It happens that the Z-score is not always going to be like 1, 2, 0. It could be like 1.5 or 1.23. Okay, happens like that. What's the population between those two z-scores? Now we're talking about a little bit different thing. We're talking about the percent. And for those of you that are like, calculus folks, the percent is the area under the curve. So this percent right here is actually the area under this curve between those two z-scores, between those two, the first standard deviation and the -1 standard deviation away from the mean. So we're looking actually at area under a curve. Now, if you do this in a calculator, you'll see the area under the curve being shaded. Do you need to know calculus to do this? No. Does it help if you're doing like engineering stats? Well, yeah, because you know what area under the curve is. So don't worry about how to find that calculus ways. Just know that that's what you're looking at. When you're looking at that percentage, you're looking at the area under the curve. Okay, so to kind of sum up everything, you're looking at a normal model, which tells us how much of the population is within certain amount of standard deviations to the mean. Our z-scores tell us how far away we are from the mean in a standardized way. And we can use the 68, 95, 99.7 percent rule to see how much of the population is between any z-score, any two z-scores, in terms of 1, 2, 3, 4 in this case. We can use that to determine, all kinds of different things that we're interested in. So in my next video, I'm going to actually go over a couple examples on how we use the normal model. This was just kind of, what the normal model is and why it's really important for us in terms of z-scores, mean, and standard deviation. All right? So next video I'll have up soon. Talk to you later, guys.